We now complete our unit on synthesis by considering a multi-step synthesis problem involving alcohol protection. Okay, so in the last lesson we considered a three-step synthesis in which we had to do an aldol plus dehydration, a reduction, and then an acyl transfer reaction to make a 12-carbon ester out of 4 carbon fragments. Now we're going to consider a variation on this molecule where we have an extra OH here on the second to right-hand carbon. And as we will see, that pesky OH is going to cause us a number of problems. So the ground rules are still the same. We want to prepare this molecule from starting materials that contain 4 carbons or less, with the exception of TBS chloride that we'll meet on the next slide. That's actually a 6-carbon molecule, but I'm allowing us to use it for this problem. Okay, so our retrosynthetic analysis. If we break this molecule down the same way we broke down the previous one, we would have the ester breaking down into a 4-carbon acid chloride plus an 8-carbon alcohol, and we would have the 2 fragments depicted on the screen. However, the problem now is that our alcohol fragment actually contains 2 alcohols, and either one or both can react with the acid chloride, and the result will be a mess. So I have depicted here 3 different products. The one on the bottom is the one we would actually want, with the left-hand alcohol being acetylated. The one on the top has the right-hand alcohol being acylated, and the one in the middle has both alcohols being acylated. So this is clearly not a good situation. So what is the solution? Well, the solution is to mask the alcohol that we don't want reacting in the acyl transfer by temporarily converting it into a different functional group that is stable to the reaction conditions, and then unmasking it at the end of the synthesis by converting it back into an alcohol. Okay, sounds simple. How do we do this? Well, the functional group that we convert the alcohol into is a silyl ether. Okay, so it looks like an ether, except on the right side of the oxygen, instead of being another carbon, there's a silicon. Silicon is directly below carbon on the periodic table. It also forms 4 bonds. So the silyl ether is called a protecting group. So the use of a protecting group adds 2 steps to the synthesis. You have a protection step and a deprotection step. So the silyl ether that is most commonly used is a tert-butyl dimethyl silyl ether, because those are stable to the reaction conditions that we generally want to use if we're going to protect an alcohol. So the way you protect it is you take your alcohol, treat it with tert-butyl dimethyl silyl chloride. Now that's a mouthful, so from now on we will call this TBS chloride. Okay, good. In the presence of imidazole, which is used as a base in this reaction. Okay, so TBS chloride imidazole converts your alcohol into the TBS ether, and instead of drawing out the tert-butyl and the 2 methyls, we will from here on in abbreviate this as ROTBS. For the deprotection reaction, once we've changed our R and made it into something else, we take the TBS ether and react it with tetrabutyl ammonium fluoride. Now this is a big thing to draw and a long thing to say, so we just call this TBAF. So TBAF will remove the silyl ether and leave us with the alcohol that we want. Okay, so protecting groups are designed so that the protection and deprotection reactions are easy to carry out and that they proceed in high yield. So that's why we use TBS ethers and not ordinary ethers. Silicon is less electronegative than carbon is, therefore it's more electrophilic. It is attacked by the neutral alcohol as a nucleophile in the reaction. It is also, because it is easier to attack it, it is possible to carry out that reaction under milder, neutral, slightly basic conditions. And the deprotection step is particularly facile because silicon and fluoride really like each other. Okay, Silicon is an element that we call very fluorophilic. So if you have the opportunity to form a silicon fluoride bond, you will, and you in fact do, and then kick out the alcohol as the leaving group. Okay, so back to our final synthesis, now in the forward direction with protection and deprotection. So reaction 1 is our protection reaction. We take our alcohol, which has the aldehyde piece on it, and we're going to protect it by treating it with TBS chloride and imidazole in THF as the solvent to give us the TBS ether. Now we do our aldol plus dehydration. Okay, so we're going to take the ketone that we need to react with this aldehyde, react it with LDA, again in THF. Then we're going to add in our aldehyde, which now has the alcohol TBS protected, so that piece is perfectly fine. Heat it up and do our aldol plus dehydration. Okay, so remember, we need the protecting group for this step, or else LDA or some other base that you might have present in solution will deprotonate the extra alcohol, and that could cause problems. Okay, then the next reaction is the reduction reaction. Okay, so in our previous lesson, we did the reduction with lithium aluminum hydride, and we did that in order to avoid 1,4 addition. Once again, the protecting group is completely stable to this reaction, and in fact, if we didn't have the protecting group there, we wouldn't be able to use lithium aluminum hydride. We would have to use sodium borohydride because that one is compatible with alcohols, and then we would have to take our chance with the 1,4 addition. Finally, the last key step of the reaction is the acyl transfer reaction that we were anticipating. We take the acid chloride plus the alcohol that now has, one of the OHs is TBS protected, the other one is still a free alcohol. We react them together in the presence of pyridine, and we get our ester. And once again, the TBS ether is inert to these reaction conditions. Our final step then is deprotection. So as we discussed previously, the reagent that's used for deprotection is TBAF. It goes selectively after the OTBS. It is neither acidic nor basic, so it's not going to worry about, and there's no water present, so we're not going to have to worry about hydrolyzing an ester. The TBF reagent selectively goes after the TBS protecting group, removes it, and leaves us with the alcohol that we want as our final product. Okay, so there's protecting groups. There are many, many protecting groups. There's protecting groups for carbonyls. There's protecting groups for amines. We are only looking at this one just to give you a flavor of what protecting groups are all about and how they are used in synthesis. But given the large number of important molecules that chemists would need to make that contain alcohols, it is important that we understand how to protect an alcohol. And with this, we also come to the conclusion of our unit on synthesis. Once again, synthesis is a vast subject. There's people who spend their lives doing this. And hopefully in the course of these 5 lessons, I've just given you a flavor of the strategy behind synthesis, the logic behind solving a synthesis problem, and some of the tactics that you put into play when actually carrying out a synthesis.